Section: Introduction. We're here to discuss the impressive capabilities of large language models, LLMs, which have been making waves in various complex tasks such as mathematical reasoning, summarization, conversations, schema induction, and solving domain-specific problems. The secret to their success lies in their ability to follow instructions and align with human preferences. Two popular methods used to enhance their performance are instruction fine-tuning and reinforcement learning from human feedback, RLHF. However, these methods aren't perfect. LLMs can sometimes create information that doesn't exist, make reasoning errors, or generate content that isn't helpful or could even be harmful. One way to address these issues is to gather more diverse, high-quality data and improve alignment with human-in-the-loop training. But this requires a lot of human effort, especially in specific domains that need expert knowledge. So, the research community has been exploring ways for LLMs to improve their own response quality without human intervention. With the rise of generative language models, prompting methods have shown to be effective and efficient. They don't require training models and can be used with black box language models through APIs. These methods allow LLMs to give self-feedback and iteratively improve their response quality, and even enhance code generations. However, self-improvement through prompting can be tricky. Humans often struggle to define comprehensive improvement goals and create detailed assessment rubrics. For instance, to improve the helpfulness and harmlessness of LLMs, we need to carefully define these qualities to guide LLMs in improving their responses. If the improvement goal is clear, simple, and well-defined, prompting can help LLMs self-improve effectively. But if we ask them to make responses more helpful, they might add unnecessary details, making the response longer and potentially off-topic. Instead, we found that asking language models to be polite, provide necessary information, and avoid going off topic yields better results. Previous methods have also noted similar observations on the effect of detailed rubrics. However, detailed rubrics are often hard to obtain. It's difficult for humans to infer and write all possible rubrics, and when the task requires domain expertise, it's impractical to scale up. To address this, we've shifted our focus from explicitly designing rubrics to implicitly learning self-improvement from data. We've noticed that the preference data used to train reward models implicitly tells us how to improve response quality. So, we've used this preference data to train a new model that implicitly understands self-improvement goals from data. We call our approach implicit self-improvement, PIT, a novel method that enables the model to learn self-improvement implicitly from data. In our approach, we reformulate the instruction fine-tuning and RLHF process. We switch the training objective from maximizing response quality for given inputs to maximizing response quality gap conditioned on reference responses for given inputs. Our method, PIT, doesn't require manual rubric design and can be used iteratively by replacing reference responses with improved responses. We've extensively evaluated PIT on 2 real-world datasets and 1 synthetic dataset, and it has shown to be more effective than prompting methods such as self-refine. In terms of alignment, which is crucial for a helpful and harmless language model, RLHF is commonly used. However, it's sensitive to training details and complicated to implement. Some researchers have used quantized rewards as control tokens to continually fine-tune policy models, while others have used reward models to filter out high reward generations for further fine-tuning. Self-improvement enables language models to improve themselves without extra human effort. The self-improved responses can then be used to update LLMs. However, these methods require environments that can provide automatic feedback, which may not always be available. Our method, PIT, doesn't require modifying model weights, an interactive environment, or explicit prompting. It's a novel approach that allows LLMs to learn self-improvement implicitly from data, making it a promising direction for future research. Section Summary. Language models, LLMs, have achieved impressive results on various tasks, but they still have limitations such as hallucinating information and generating unhelpful content. Prompting methods have been effective in self-improvement, but defining comprehensive improvement goals and creating detailed assessment rubrics can be challenging. In this paper, the authors propose a novel approach called implicit self-improvement, PIT, that utilizes preference data to implicitly learn self-improvement goals from data, eliminating the need for rubric design. PIT outperforms prompting methods and does not require manual rubric design or additional data. Section: Method. Let's break down the method used in this research. The researchers used two types of models, policy models and pairwise improved training, PIT, models. Policy models generate responses based on given inputs, while PIT models take the given inputs and reference responses to generate improved responses. To train these models, the researchers used a method called reinforcement learning from human feedback, RLHF, which involves three steps: supervised fine-tuning, reward model training, and reinforcement learning. Let's imagine we have a dataset, which we'll call D. This dataset contains three types of data: the input prompt, X, the worse model generation, Y_L, and the better model generation, Y_W, all annotated by humans. The researchers divided this dataset into three equal parts, each used for one of the RLHF steps. The policy model, denoted as M_P, is trained to generate a response, Y_P, for a given input, X. The PIT model, denoted as M_PIT, is trained to generate an improved response, Y_PIT, for a given input, X, and a reference response, Y_ref. The first step of RLHF is supervised fine-tuning, SFT. This step only uses the input prompt, X, and the better model generation, Y_W, which could also be human-written responses. The policy models are trained by maximizing the likelihood of Y_W. For the PIT models, they also include Y_L in the training. However, the researchers found that using unlikelihood loss caused performance degradation, so they only used likelihood loss when training the PIT models with SFT. The second step is reward model training. The reward model is used to judge the quality of a response and is crucial for reinforcement learning. The reward model, denoted as R_P, maps an input, X, and the corresponding response, Y, to a scalar value, R. The reward model is trained by maximizing the reward gap between Y_L and Y_W. Unlike R_P, the reward model for PIT, denoted as R_PIT, focuses on the gap, R_gap, between responses. Therefore, R_PIT needs to learn the difference between R_W and R_L from the training data. The researchers also noted some drawbacks of using R_P to compute R_gap. First, R_P converts the pairwise preference data to pointwise scalar rewards, which introduces additional noise. Second, the extra subtraction operations increase the variance of R_gap, which may harm the stability of reinforcement learning. Lastly, if R_gap is computed directly with R_P, it results in zero gradients during reinforcement learning, which is not desirable. In contrast, the researchers found that R_PIT returns a negative reward to penalize repetitive behavior, which is beneficial for self-improvement. Section summary. Policy models trained with RLHF generate responses for given inputs, while PIT takes the given inputs and reference responses to generate improved responses. To train PIT, we reformulate the RLHF training objectives by following the steps of supervised fine-tuning, reward model training, and reinforcement learning. In supervised fine-tuning, we maximize the likelihood of the better model generation, while in reward model training, we maximize the reward gap between the worse and better model generations. Section: Reinforcement learning. Let's delve into the concept of reinforcement learning, RL. In simple terms, RL is a method that helps us find a strategy or policy that can maximize rewards over time. This aligns large language models, LLMs, with human preferences. The goal of RL is to optimize a policy model, which is initially set to a model trained in supervised fine-tuning. This model remains constant during the RL process. To prevent drastic changes in weights and reward hacking in RL, we use a method called KL divergence. Now, let's talk about a specific type of RL called curriculum reinforcement learning. Unlike the standard RL equation, a method called PIT, policy iteration training, aims to enhance a reference response instead of creating a response from scratch. This means that RL for PIT uses both the input and the reference response simultaneously. The challenge here is deciding on the reference response. A straightforward approach is to use the responses provided in the dataset. However, since PIT aims to improve the responses of the RL policy model, and the responses in the dataset are not sampled from this model, we need to perform another round of RL, In this round, the reference response is sampled from the policy model. This flexibility allows us to perform multiple rounds of RL to further improve PIT. For instance, a third round of RL can sample the reference response from the PIT RL model, which allows PIT to enhance the already improved RL policy model responses. In theory, this process could be repeated indefinitely, and we refer to this as curriculum reinforcement learning. It's important to note that the first round of RL in PIT is crucial. This is because optimizing the second round of RL in PIT directly is quite challenging. The responses sampled from the RL policy model are already of high quality, and improving them is harder compared to the responses in the dataset. Therefore, we need curriculum reinforcement learning to successfully optimize the second round of RL in PIT. If we remove the first round and directly optimize the second round, PIT fails to improve the RL policy model responses. Also, training PIT solely on the first round of RL leads to failure, as PIT never encounters data sampled from the RL policy model. To create a smoother curriculum, we could even add several intermediate rounds between the first and second rounds. For instance, we could sample the reference response from intermediate checkpoints of the RL policy model, as their responses are less perfect and easier to improve. In our experiments, we use the first and second rounds of RL in PIT for optimization, as we find that the dataset does not require more rounds or intermediate rounds. Finally, let's discuss the inference process. Given an input, we first sample a reference response from the RL policy model. Then, we can obtain an improved response from the PIT RL model. This improvement process can be repeated indefinitely. For example, we could get further improved responses by feeding the previous improved response back into the PIT RL model. Section Summary. Reinforcement learning, RL, is used to find a policy that maximizes rewards over time, aligning language models with human preferences. In the context of PIT, policy improvement through teaching, RL is employed to improve a reference response instead of generating a response from scratch. This is achieved by sampling the reference response from the policy model and iteratively optimizing it through curriculum reinforcement learning. Section: Experiments. We conducted a series of experiments to answer two main questions. First, can our approach enhance the quality of the original response? Here, quality is determined by the preference data. For instance, if the preference data indicates a desire for a more helpful and less harmful response, then a higher quality response would be one that is more helpful and less harmful. Second, can our method improve the response more effectively than prompting methods like self-refine? We used 3 different datasets for our experiments. 1. The hydrogen hydride RLHF dataset from Anthropic, which is available for research purposes. This dataset includes 161,000 conversation pairs between humans and AI assistants for training and 8,550 pairs for testing. The goal of this dataset is to train an AI assistant to be helpful and harmless. It has 2 subsets, one focused on helpful responses and the other on harmless responses. For our experiment, we only used the helpful subset, which we divided into 3 equal parts for supervised fine-tuning, reward model training, and reinforcement learning. 2. The OpenAI summary dataset, also available for research purposes, contains Reddit posts and 2 summaries for each post with human preferences. It includes 92,900 training data and 86,100 validation data. Like the HHRLHF dataset, we divided the training dataset into 3 equal parts for supervised fine-tuning, reward model training, and reinforcement learning. 3. We also used synthetic data to test the instruction following abilities of language models. We used PaLM-2, Unicorn, to generate 13,000 synthetic data. Each synthetic data includes a question with multiple requirements, a satisfactory response that meets all requirements, an unsatisfactory response that only meets some requirements, and a reflection on how to improve the unsatisfactory response. We divided the synthetic data into 3 equal parts and used 128 examples for evaluation. We used the pre-trained PaLM-2, Bison, as our backbone language model and reward model. We found that smaller models had poorer generation abilities, and larger models were too expensive to train. We trained our models on TPU versus 4. We compared our method, PIT, with other self-improvement methods using prompts, specifically self-refine. Self-refine uses prompts to instruct the model to reflect on the current response and give feedback to improve the response, then asks the model to give an improved response based on the feedback. For evaluation, we used third-party language and reward models that are allowed for research purposes. These models are sensitive to the rubric and need carefully designed prompts to achieve good performance. To get a reliable evaluation, we used both third-party models and human evaluations when the two evaluations disagreed. We found that GPT-4 had the highest agreement with the ground truth validation data compared to ChatGPT and PaLM-2, Unicorn, so we used it as the representative of third-party language models for evaluations. We used Debrda Large, 304M, trained by Open Assistant as the representative of reward models because it uses different model architectures and full training data, reducing the risk of reward hacking during evaluations. It performs similarly to GPT-4 on the ground truth validation data. We found that our method, PIT, generally outperforms the other method, as expected. We also observed that the reward is negative when two responses are identical, indicating that PIT penalizes repeating responses. Section Summary. The experiments in this paper aim to answer two questions. 1. Can our method improve the quality of the original response based on preference data? 2. Can our method outperform prompting methods like self-refine? 3 datasets were used: Anthropic, HHRLHF, OpenAI, Summary, and synthetic data generated by PaLM-2. The models were trained on TPU-v4 and evaluated using third-party language models and reward models, with human evaluations used when there was disagreement. Section. Results. We've conducted a series of experiments to evaluate the performance of our proposed method, PIT, in comparison to other models like GPT-4 and Debrda. Due to the high cost and slow speed of GPT-4, we limited our evaluation to 128 examples for GPT-4 and 1,000 examples for the Debrda reward model. To minimize noise, our reward model declares a tie when the rewards for two responses are very close to each other. In practical terms, this means that if the difference between the rewards of two responses falls within the range of 0.45 to 0.55, the model considers it a tie. We first generated responses using our model and then applied self-improvement methods to enhance these responses. We found that our method, PIT, consistently improved the quality of responses across 3 datasets, outperforming the original responses by a margin of 7.2% to 33.59%. This was true regardless of whether we used GPT-4 or Debrda as evaluators, demonstrating the effectiveness of our method. We also compared our method with another technique called self-refine. Both GPT-4 and Debrda agreed that self-refine improved response quality. However, GPT-4 showed a slight preference for self-refine, while Debrda favored our method. We conducted human evaluations to resolve this discrepancy and found that humans preferred our method over self-refine by a significant margin of 23.53%. We also explored the impact of different temperatures on the performance of our method. In this context, a higher temperature represents more diversity and randomness, while a lower temperature indicates more coherence and quality. We found that our method performed best at lower temperatures, which aligns with our initial assumption that self-improvement should focus on the most reliable improvement direction rather than randomly exploring different directions. In conclusion, our method, PIT, consistently outperforms other techniques across different datasets and under various conditions. It improves response quality, aligns closely with human preferences, and performs best under lower temperatures. Section Summary. We evaluated the performance of our method using GPT-4 and Debrda evaluators, with 128 examples for GPT-4 and 1,000 examples for Debrda. The reward model gives a tie if the rewards for two responses are similar, and we found that our method consistently improves response quality by 7.2% to 33.59% compared to the original responses across 3 datasets. Additionally, we observed that low temperatures, 0.4 to 0.6, are preferable for improving original responses using our method, while high temperatures, 0.6 to 0.8, are more effective for self-refine. Section. The effect of curriculum reinforcement learning. We've been exploring the impact of curriculum reinforcement learning in our model, which we refer to as PIT. In this process, we apply reinforcement learning twice, each time increasing the difficulty level. The first round of reinforcement learning is designed to enhance the model's ability to improve the original responses, while the second round focuses on improving the responses generated by the model itself, which we refer to as MPR responses. To understand the significance of this two-step reinforcement learning process, we experimented with two additional versions of the PIT model. One version was trained using only the first round of reinforcement learning, while the other skipped the first round and went straight to the second. When we compared these two versions with the original PIT model, as well as with the self-refinement process conducted by MPR, we found that both versions only marginally improved the original responses and fell short of the performance of the original PIT model and the self-refinement process. This outcome was expected. The first version of the model, which was trained only on the first round of reinforcement learning, didn't learn how to improve the original responses and was only trained on simpler, ground truth data. The second version, on the other hand, was immediately faced with a more challenging optimization problem, which is evident from the fact that the original responses were significantly better than the responses generated by the model. We also observed the rewards given during the training process. The model that only used the second round of reinforcement learning struggled to improve the original responses due to the challenging optimization problem. However, the PIT model was able to make progress thanks to the first round of reinforcement learning. Knowing when to stop the self-improvement process is crucial. In theory, this process could go on indefinitely. The decision to stop could depend on various factors, such as a fixed time limit or the significance of each improvement. In this study, we focused on the quality of the responses and whether they improved with more iterations of the self-improvement process. To measure this, we used ELO scores. We used the PIT model and the self-refinement process to improve 1,000 original responses over 5 iterations. We then compared these responses using the Deberder reward model. The results showed that the PIT model consistently outperformed the self-refinement process, regardless of the number of iterations. However, the quality of the responses and the number of iterations did not have a simple positive correlation. This suggests that we need to be careful when designing the stopping conditions in real-world applications. Sometimes, the self-improvement process produces the same responses as the previous iteration, which could potentially serve as a stopping condition. We also found that the order of comparisons can affect ELO scores, so we shuffled the comparisons several times to ensure our conclusions were not influenced by randomness.